It's an immense pleasure to have Gerard Toft from the University of Utrecht as our speaker. I think that his interest for science started from when she was very small. Also because he belongs to a family of scientists. And he won the Nobel Prize in Physics in 1999. But what I think is more important for his Nobel Prize is that he got because of his PhD thesis. And this is a message to our PhD students. Don't lose the hope to get a prize at some point. So at that time, for the PhD thesis, he was studying what is now called, what are called the Yang-Mills theory, that at that time were not taken very seriously from many people. So he decided to go in a topic that was not trending in that time. So in his first paper, what he analyzed is the massless Yang-Mills theory, and he showed that it is possible to renormalize these theories. In this thesis, in this paper, he also found some relations between amplitudes that were afterwards generalized by Slav and Taylor, and that are known today as Slav-Taylor identities. And for the second paper, it was natural to extend the massless case to the massive case from spontaneous symmetry breaking, showing that also in that case, the theory is renormalizable. So that in this paper, he also developed the technique of dimensional regularization that is central in all our current calculations. So for this work, he got the Nobel Prize in Physics for, if I find it, for elucidating the quantum structure of the electroweak interaction in physics. And this is what makes the standard model unreasonable theory. But this is not the only thing that he has made. For instance, he discovered the asymptotic freedom that makes sense to QCD. That contrary to many people were thinking about, QCD is getting stronger at larger distances, contrary to what happens for gravity and electromagnetic interactions. Besides the Nobel Prize, he has also gotten a lot of prizes like the Wolf Prize, the Lawrence Medal, the Spinoza Premier, the Franklin Medal, and many honorary doctorates. He belongs to several academies of science. He also made important contribution for discovering that the SUN gauge theories in the Lorentz N limit are simpler than expected. He has been also working in instantons and magnetic monopoles, and recently he's working on black holes and how to reconcile quantum mechanics with gravity. He even has one asteroid on his name, and he has written also some fiction books. So it is a pleasure to have you here in our institute. So please, go ahead.
Thank you very much for your kind introduction. I'm delighted to see so many people come here to listen what I have to say. My talk will be about black holes, but seen from a theoretical point of view. Black holes are playing a role that in theoretical physics is as important as the role they actually play in astrophysics and in physical space-time that as we know it. I'm focusing now on what they are telling us about the theory of interactions among elementary particles, among fluctuation of space and time itself. All these questions are very important for theoreticians to understand. There are many deep, ununderstood riddles still left, so we have still lots of work to do. And perhaps black holes can help us here. I'll try to explain in what way they do that. So, I just saw here some other pictures of the standard model. There are many ways in which you can describe our present stage of knowledge about the interactions of these subatomic particles. And They've been put together now in what was called a standard model. I like to, since I was already interested in physics as a kid, I like to look at the standard model as a toy, a delicious toy that has been discovered during the 20th century. The toy contains several boxes or bricks that you can put together, and out of those bricks you can make anything you like in nature. And you see different kinds. One set of bricks comes in 3 varieties, 3 boxes which look practically identical. Only the top of these boxes is much heavier than the lower two, and the middle one is a little bit heavier than the lowest. So these boxes have a different weight, but otherwise they look nearly identical. And this, at the same time, this picture, maybe the light can be lowered a little bit, so the picture becomes a little bit clearer. Is that possible? Anyway, they represent today's understanding of subatomic particles in a beautiful way. It is a very coherent picture of all interactions that we have, and it is nearly complete in the sense that it describes almost everything we know about the subatomic particles. However, there are some things we don't know about the subatomic particles, and those are definitely not well described by this model. Of course not. We can do experiments and observations, but we can only write down what we see. We cannot write down what we don't see. And there are things we don't see which are not properly included in here. Though things you don't see, or not quite. There is a substance that we call dark matter, and dark matter is literally something that's dark and therefore doesn't show us where it is, but it does show its presence indirectly in terms of its gravitational field. So there are particles floating around in the intergalactic world or in the galactic region of space, and these particles do betray their presence by their gravitational fields. They force stars and planets to be attracted to each other more strongly than one would have expected if they only consist of matter that you see in this picture. If this were all, then the galaxies wouldn't rotate so fast and wouldn't attract each other so much as what they are actually seen to be doing in the telescopes of the astrophysicists. So the dark matter is still missing. Not only dark matter, but also there's a concept called dark energy. It has, in some sense, the opposite effect. Energy in the universe, well, it's difficult to explain where it comes from. We just put it there, and it was already discovered by Einstein that there was a freedom to say something about the energy content of empty space. And whatever you put there has a gravitational effect, but it's more repulsive. It forces galaxies and stars to move away from each other. This effect accumulates when there's lots and lots of space, because that energy is just proportional to the amount of space we have. So the bigger the universe becomes, the stronger this effect is. So the universe expands exponentially, actually, because of dark energy. But we don't really understand the source of this. There is no source needed, but there's a theoretical source needed. There should be a theoretical argument explaining to us why this dark energy is there and why it has the strength that actually is seen there. This strength is ridiculously small, ridiculously weak. So dark energy is a very, very tiny effect of empty space-time. That makes it even more mysterious, because if the effect would be in any way described or caused by elementary particles, it would have been much stronger than it actually is now. So there are mysteries here not properly understood, which means theoretical physicists haven't completed their job. There are still many questions that we have to answer. And the great big question that's left over for us that we want to answer very badly is the question of the gravitational force. You see the particles in this model described are responsible for various forces. These particles here, the white particles here, are responsible for the weak force. The colored particle belongs in the same structure, so it belongs there as well, but that describes electromagnetism, it's the photon. Here are the color forces, and represented by 8 particles called the gluons, and you would like to understand where these how these particles originate, and well, we have all the equations of these fields and particles. We do not really understand why there's particularly this combination of particles in the standard model. There's some mystery here. Not only the strength of the interactions are not quite understood, but also the question, why are there 3 of these boxes? Why not 5? Why not just 1? Why is the number odd? All these questions are also not completely answered. So yes, but the most basic unanswered question is the gravitational force. Gravity seems to be the most fundamental force of all, so you might say it's the easiest force. You understand immediately that you're being pulled downward by planet Earth. So how complicated can it be? That doesn't sound very complicated, and it was the first force really understood in detail in terms of its equations by Isaac Newton, and then later refined by Einstein to match his other theories of relativity. And all that is understood. So why am I listing gravity as an understood force here? Well, these particles are also subject to quantum mechanics. Quantum mechanics tells you how really these particles behave when a force is put on them, and when they interact with each other, when they collide, when they decay. All that is controlled by quantum mechanics. More to say about this yesterday, so I won't repeat myself too much, but quantum mechanics is a very essential ingredient in the mechanical laws of these particles. How does quantum mechanics work when gravity is present? So how does gravity get modified by adding quantum mechanics? This is a deep mystery that we have not understood the way we like to understand it, and the way we understand the other forces. The biggest problem with gravity is when the distances become very, very small. I'll explain that in more detail in a moment. But when the distances become very, very small, much smaller than the distances these particles usually have with respect to each other in our investigations, many orders of magnitude smaller, then the gravitational force increases faster than all the other forces. It increases so fast that at some point it becomes uncontrollable. That's where we are interested in the equations. So the uncontrollable part of the equations, well, the word says it already, is something we don't understand. And we wish a better understanding there. Indeed, the standard model is a huge joint achievement of the 20th century. It's a crown on the science that we've all been doing around that time. And we all love the standard model. It's a very solid piece of information. The equations seem to work with fantastic accuracy. So yes, there's a lot of things that I do understand about the model. There's also some mysteries that we do not quite understand. One reason why the standard model is now so perfect and works so well is that we have lots and lots of experiments that can be done. The last experiment is the LHC, the Large Hadron Collider, which checked how particles interact with the highest possible energies, and even at those very high energies, the particles are still described very, very well by the standard model. In fact, the LHC added one ingredient which had not yet mentioned, this particle here is the Higgs particle. That was still the only theoretical part in the standard model that had not yet been checked explicitly, but now we have experiments that also show that particle to exist more or less the way it was predicted. And now we know much more. We know exactly what its mass is. That was not known before the LHC. And now we know exactly what its mass is. And also, we now realize this mass is a very special value. There's something very important about that mass that we're still not quite grabbing correctly. Now, and from here we want to go on, but there's one big problem when we want to produce better theories. And that is, yes, we have many ideas in our mind about better theories. We have a sort of grandiose vision of what the theory should look like that doesn't have any of the difficulties. For instance, we have theories about what the source of dark matter could be, what the source of dark energy could be. We also have all sorts of ideas of how to quantize gravity. But those ideas do not work completely. They all have their weak points. And that is an even more important problem with all those ideas. It is very difficult to check them experimentally. So the Standard Model itself was so good that with all our machines we could check it in great detail. Thousands of experiments were done to check independently how the Standard Model works, and that's why the model is so good. It has survived all these experimental checks. But now when we think of extending the Standard Model to go beyond what we know before, it's very hard to do any experiments. So we hope that the LHC will give us some experimental results that tell us what a possible next step would be, but it hasn't revealed any of that. It just said the Standard Model still works even to high energies, so we are sorry, but we are not going to give you anything new. And that's a problem, because now we don't know how to proceed. Well, we can proceed in our imagination. And that's, for lack of anything else, that's what we have to do now. We can do indirect experiments, so experimental physicists are still having lots of work to do, because they find still things they can calculate and check, and maybe they'll get indirect indications about how to improve the Standard Model. But that hasn't worked so very well up till now. That means that we still do not have good clues on how to continue, except for doing it in our imagination. So now we use our imagination, and theoretical physicists are good at using their imagination, but not quite as good as they think. So we imagine all these great equations, but those equations do not tell us why the Standard Model has its shape as it has. It doesn't. The equations do not tell us why the interaction strength of the Standard Model particles are as they are, and the equations do not really close properly as well as they should. Within the Standard Model itself, the equations are perfect. They show everything with great detail. But beyond that, they become vague, and the new equations that we have to put in their place do not close as well as we had before. So we have great big problems. The problems were such that some people became very critical. For instance, there's Lee Smolin, who had also ideas about string theory itself, about Standard Model itself, and then he become a dissident in a sense. He wrote a book, There's Trouble. And he thought there's trouble in physics, because I'm imagining all these new theories, but we have no way to check them. And probably all our imaginations are wrong. And I tend to believe that what many theoretical physicists imagine to be able to do, it doesn't have to be true. And in fact, you might ask the opposite. Why do they believe so strongly that some of these theories may well be true? In particular, so-called string theory and superstring theory, which has been getting very strong support by many investigators. But why do they think these theories are true or may be true? And some of that is psychology, but there are other reasons as well. So Lee was very critical to what they were saying, but part of the criticism, I think, also is unwarranted, and I think the string theorists are doing a marvelously good job. They are inventing equations with lots and lots of effort. The mathematics becomes extremely complicated, but the equations that they get do seem to make sense all by themselves. They do seem to form one great big theoretical construction. The only problem is the equations still don't quite close, and the construction still doesn't quite work, and unfortunately they don't tell us anything that can be checked directly. That would be things that could not be obtained by any other more basic theory as well. So Lee's thought there's big trouble there. I agree that we should be careful and watch our steps. When a set of equations is beautiful, that doesn't mean that it is true. And in fact, there have been other people making the same observations. I'll not waste much time with these books. These are people who are very much more critical even, and start to say that science is now going into a dead end, and we're all following crazy ideas, and we are about to leave the era of science altogether. We are doing things that make no sense at all. Some people think that I do not agree with, but I do see some of their points, which is that we are not in the same situation as when the Standard Model was being formed. We do not have the experiments. Maybe all these extra things that we all believe in are not at all representing reality. Maybe the real world is something totally different. And I'm keeping that in mind as a warning. We don't know for sure that string theory is going to be the correct theory at all, or actually any of its alternatives. So yes, the key question, which is found today, is very difficult to answer, and we want to have an exact description for how to incorporate the gravitational force. That's the main thing. We just focus on gravity, and the general belief is, and there are many reasons to believe that very seriously, if we find answers to how to quantize gravity, how to put gravity in a completely satisfactory way as an ingredient of the standard model, then we'll be ready to answer all these other questions. And maybe we'll be able to say why the other forces have the strength they have, and many of the other questions. I like to compare the situation a little bit with the following metaphor. Imagine a biologist who wants to study rats. So he puts a rat in a big cage, and he's asking himself, how intelligent is this rat? Now, the rat has been in many other experiments before. And every time an experiment was done with the rat figured out what to do to get its food. And after every experiment, the next experiment was a little bit more complicated. And now this rat sits in a box again, and he sees the familiar things. He sees switches and buttons that he had to press before, and he sees delicious food hanging on the ceiling here. So at the ceiling has his peanut, and the peanut tastes, and he knows that peanuts taste very good. So he wants to eat the peanuts. The only problem is, what should he do? Should he use the swing? Should he start to jump on the ladder? Should he push this button? Should he pull that lever here? What does he have to do to get the peanut? Suppose that the peanut is so high up that he can't jump to get it. I think in this picture is a little bit exaggerated. He can easily jump and get the peanut. But suppose that's also impossible. What should he do? And the rat knows in the past he always succeeded in getting what he wanted. And now he sees something that he wants very badly and he can't get it. And the general feeling that the rat feels, he is too stupid. So he's too stupid. He knows if he had been smarter, he would have had his peanut long ago. But he isn't. He's too stupid to solve the problems that he sees around him. He just can't argue. He can't memorize what he thought before and join all the information he has together into one prescription about how to get this peanut. He feels he's too stupid. That, I think, is exactly what we feel today as well. We want to solve problems in everything, but it's too difficult for us. We feel we are too stupid to solve the problem. And it really is that. So we don't need the experiments in principle. We have all the information. We have all the information. The standard model contains lots of information that we could use. So we have lots of levers and buttons and swings to try. We can do lots of experiments. Also, we can watch the fluctuations in the distant universe and watch how the galaxies form and go. So we have all the information. Why can't we quantize gravity? Just because we're too stupid. So let's try to see what else we can do. There are actually quite a few different theories for quantum gravity. There's so-called loop quantum gravity, which is the idea that you have, as Einstein said, space and time are curved. There's a deep mathematical definition of curvature. The mathematicians say, take some closed curve, a loop, and then ask, how does a curve loop locally, and how is it closed? For instance, take a triangle. A triangle is also a closed curve, but now if you take the three angles of the triangle and you add them all up, and when you get 180 degrees, then you know that the legs of the triangle will close. The triangle will close perfectly as a triangle. If the three angles do not add up to 180 degrees, there's something wrong with the triangle. It doesn't close. Unless the triangle sits on a curved space, then you can have angles not adding up to 180 degrees, and yet the triangle closes. So that's extending that theory into a big scheme is called loop quantum gravity. It works beautifully, but then people get astray. They don't know how to pull the last switch. And there's a similar theory called asymptotically safe gravity. It's the idea that if you go to distance scales so small that gravity ought to explode completely, it doesn't explode. The gravitational force reaches some limit, and then the theory becomes safe against scale transformations. There's an idea of space and time to replace space and time by little flat regions that you glue together. You take many flat triangles, you glue them together, and then you build up space and time like that. That's called dynamical triangulation. There is, of course, string theory, I already mentioned before. String theory now seems to be holding the best cards of all. And they're very proud of that, and they shout away all the other guys because they think they have the best cards. But having the best cards doesn't mean, at least to me, it doesn't mean that you have the correct cards. There can still be something very basic wrong with the theory. But then they continue, and with their imagination, they write down M theory, they invent new mathematical manipulations called ADS-CFT. I won't bother you with what all this really means. And there are numerous other attempts which are even vaguer than what I wrote down here. So yes, there are many ideas of how to call it, but none of them is completely successful. And actually having no clue from experiments is perhaps worse than maybe experiment. If we had experiments, the experimentalists would tell us you're on a completely wrong track, you should think about it differently. And then experiments would tell us how we should think about things. And maybe that will lead to much more satisfactory answers. The problem I like to see it is that in the entire 20th century there have been tremendous developments, and we have been spoiled by the riches that were found in the physical world, both theoretically and experimentally, in the 20th century. And if I try to understand why was that the 20th century was so successful in our science, I think what was discovered in the 20th century was not only these scientific facts, but the entire scientific method was being discovered. It was discovered that you have to ask very precise questions about what happens when an experiment is being done. You have to ask questions not only about the experiment, but also how do we actually observe things? What is the role of the observer in an experiment? And this you have to think about very deeply and very carefully. And when you do that right, you discover new ways of phrasing things and new ways of actually doing experiments. So you can combine all this knowledge together, and then you'll find new features you did not know before about how particles interact. So this is a very important discovery that accelerated science in a big way in the entire 20th century. But by now, this discovery is 100 years old. It is time for the scientific method itself to be replaced by something better. How do we do that? Now, we tended to say, if you can't do experiments, you don't do experiments. You just think very carefully about how theories ought to be constructed. But that is very dangerous. That can lead you into believing things which are simply not there. And so my belief is that actually you can do that. You can imagine purely theoretically how to proceed to the next sophistication of the standard model, but you have to do it extremely carefully and extremely precise and logic. Now, people tend to play with models, and they're called toy models. Now, I also play with toy models to sharpen my instruments, but maybe the toy models are misleading, and you have to investigate the real thing. But you have to investigate the real thing as accurately and carefully as you can. And there, I think, when I see people write down models and think about their models, they are not accurate enough. And then I think the ideas that they come up with are running astray, and they're not as good as they themselves seem to be thinking. So I start from the very beginning. And let me start indeed with the beginning. Let me start with the gravitational force. Einstein made a terrific contribution in understanding gravity. That's of course not very surprising that I say this. First of all, gravity is a very fundamental force. It acts only on mass and nothing else. There's no charge or anything that makes something feel stronger or weaker with gravity. It's not only the mass of it itself determines how strongly it interacts with other masses. Gravity never repels, with the exception perhaps of dark energy, but that's another story. But the gravitational force between objects always attracts. And also, at the same time, we have Einstein's theory of relativity. Now, Einstein found in 1905 how to formulate the theory of special relativity, where he got everything relativistic. That is to say, forces are relative and velocities are relative, everything except for the gravitational force. And he realized, as soon as he had finished his theory, he realized there's one force that I haven't yet taken into account, that's gravity. How can I make gravity also relative, in the same sense that electromagnetism obeys relativity theory? Gravity didn't, or not quite. Something was not yet right in his theory. And so, knowing that something was not right in his theory, Einstein could then make the next step and find out how to close the gaps. He knew enough about gravity and knew enough about relativity to be able to close the gaps. Today we have a similar situation, but we don't know enough how to close the gaps. That's the big difference. And so what Einstein found was that space and time are curved. So not only they're relative, when Einstein talked about relativity itself in 1905, space and time themselves are still basically featureless. Now it says there are features in space and time that, as a consequence, make that the angles of a triangle do not add up to 180 degrees anymore, but sometimes something else. But there's not only curvature in space, and that is indicated in this picture here, that you see that heavy objects such as the Earth is surrounded by space and time that is slightly curved due to the presence of planet Earth. But there's also curvature in space-time. Space and time together form a new element of curvature. And that curvature is illustrated in this picture here. You see here 3 clocks. The 3 clocks are identical clocks in all respects. So when you put them together, the clocks will, each 3 will tick exactly as fast as the other 2. So these clocks always show the same time. Once you set them at the same time, they always show the same time. But now I take them apart. I put one clock very close to the Earth, on the Earth's surface, one clock very far away, and one clock somewhere in between. Then you'll find that in spite of these clocks being constructed identical, the clock far away will tick faster than the clocks close by the Earth. In fact, the clock closest to Earth goes much slower, and this one goes fastest, this one goes at the intermediate speed. So the speed at which the clock ticks changes. Now we can close the curve. We can pull this clock, we can take this clock and put it away from that clock for a while, let it run for a year, and then bring it together again. That is a loop in space-time. And now you see that now there's a mismatch of the time that the 2 clocks show. So there's a loop in space-time. When you run the clock around the loop, there will be a mismatch in the time that it shows. That is just like the angles of a triangle not adding up to 180 degrees. So, so we say this is curvature in space-time. This allows us to describe much more about the gravitational force. Let me see what the gravitational force does to a heavy object, a very heavy object. And a very heavy object is, for instance, a very heavy star. The Sun contains thousands times more mass, million, I think, than the planet Earth itself. So the Sun is much heavier than the Earth. So gravity acts much stronger on the particles in the Sun than it does on Earth. On Earth it's already pretty strong, we feel it every day. On the Sun it's much stronger. So now we can ask, what effect is there on the planets, on stars such as the Sun? Well, it makes that the interior of the Sun is being compressed. All the particles in the Sun are pulled in the same direction, inwards. So at the center you have a large, high pressure. That pressure at the center of the Sun is so high that it gives the needed counterforce. So the pressure in the Sun blows the Sun out again, so there will be a new equilibrium. The Sun actually owes its spherical shape to the gravitational force around it. The gravitational force, it generates itself. But then the Sun stops contracting, so the Sun gets a, whenever, for instance, if the Sun gets out of fuel, if the nuclear fuel in the Sun has burned completely, hydrogen is nuclear fuel in the Sun, so when all hydrogen has been burnt, there's only helium and heavy elements left. Then the Sun will no longer produce the heat needed to give the counter pressure, so the Sun will shrink. However, when it shrinks, it increases the pressure inside, and then suddenly at some point the pressure will become so high that also helium starts to burn and make heavier elements. Then the Sun will actually expand again, and it will actually not shrink any further. The outer layer of the Sun will expand. The Sun will become bigger rather than smaller after hydrogen has burned up. But that's a more complicated combined effect. You can, however, ask the question, suppose that I put much more matter in the Sun. Suppose there are some stars which are 10 or even 100 times heavier than the Sun. So what happens if such a star contracts? Then the gravitational force is much stronger. So those heavy stars will be contracted much further. But when something is contracted further, the gravitational field also increases, because the gravitational force is inversely proportional to the square of the distance. So if something contracts, the distance between the particles becomes shorter, and so the gravitational force will increase. Perhaps that increase in the force will be such that the pressure caused by the nuclear fuel inside the Sun will not be enough to give all the counterforce. Such a star might continue to implode, and when it does so, well, it eventually go on and implode into what? Well, that could be a point. Does the Sun go into a point? Now, Einstein would say, wait a second here. If something becomes so small, the gravitational force becomes so large that the escape velocity of matter at the surface of the Sun will exceed the velocity of light. That's impossible. Nothing can exceed the velocity of light. So you run into what you might call a contradiction, a paradox. What happens? Einstein didn't even think of that question immediately after he made his theory of general relativity. He only thought about it later. But there was a well-known astronomer who did think about the question, and the astronomer was a German astronomer by the name of Karl Schwarzschild. And Schwarzschild wrote a paper in German über das Gravitationsfeld eines Massenpunktes nach der Einsteinschen Theorie. It's about the gravitational field caused by a point mass. A point mass meaning an object is very heavy, but for all practical purposes we can consider it to be a point. So it has no spatial extensions at all. We can compute the gravitational field everywhere around the particle there is vacuum. And Einstein tells you exactly how the gravitation, what kind of equations that gravitational field obeys. And Schwarzschild said, wait a minute, in the spherically symmetric case, these equations are so easy, I can solve them explicitly. So Schwarzschild said, let's solve the equation explicitly and see what happens when a star contracts to a point. He didn't get it quite right. He had the equations right, he had the answer right, but the physical interpretation of the answer he had not quite right. There was one thing he didn't understand, which was that as soon as the center, the matter in the center becomes so contracted that the space velocity becomes equal to that of light, you can't get any further. So he thought that must be when I've reached the point, the center. So he changed the coordinates that he's using such a way that whatever happens when the light can no longer escape, I put in that single point. And he learned from Einstein you can choose your coordinates any way you like. So let's choose our coordinates this way, that we have all the unknown physics at a central point, and that's surrounded by a gravitational field that he, Carl Schwarzschild, could compute. The solution became very famous, but later we decided to look more carefully at that central region that Schwarzschild didn't quite correctly describe physically. His mathematical equations were totally correct, so he understood how to solve linear equations, yes, but what's the physics at the center? Well, let's concentrate on that now, and imagine again a very heavy object. For simplicity, I again take planet Earth. Space and time around planet Earth are curved, so if you carefully see that the circles do not quite sit in the middle, so there is some curvature in space-time surrounding planet Earth. But now, suppose that planet Earth would contract under its own gravitational field, what would happen? And amazingly, the correct physical description of what happens is that space and time get curved so much that the curvature somehow doesn't allow for any central point at all, but it curves backwards. In fact, what you have to say is it continues there, space and time will continue, to form another universe. What does that mean? Well, what you really have to say is that there are now two universes, and somehow the space and time form a wormhole that connects one universe to another universe. Mathematically, that is a more precise way of phrasing the Schwarzschild solution than what Schwarzschild himself did in his first paper. But remember, he was a pioneer. He was investigating something for the very first time. When you are a pioneer, you don't get everything right immediately. But he still was a very good and smart astronomer. Unfortunately, he died only a few months after he wrote his paper, so he never witnessed what happened, what this paper did in theoretical physics. It did quite a lot. This strange situation cannot be true, by the way, because if the Earth shrinks, how can it generate an entire universe? That cannot be right. Physically, it makes no sense whatsoever. So something is very wrong about this picture as well, and we have to worry about what it all really means. Let me look at it more carefully again. Here, universe 1 and universe 2, and somehow there are two universes which are then connected by a wormhole. That would be the case if the Earth didn't somehow be allowed to collapse to a point. But what we now say is, this is a black hole, or is it a wormhole? Well, there is a problem with saying that this is a wormhole, because even worms will not be able to get through this hole. Why not? Well, this red circle in the middle actually isn't a circle, but it is a sphere, and that is because I drew this space-time here as a two-dimensional space and one time coordinate. But actually it's 3 dimensions. So there's 3 spatial dimensions, and there's time. And in 3 dimensions, this is not a circle, this is a sphere. But the sphere is called the horizon of the black hole. If you come to the center closer than the horizon of the black hole, then you reach this wormhole. But you can't get closer. Why not? Well, remember those clocks I talked about. Clocks here go fast, clocks close to the center go slower. Well, ladies and gentlemen, this clock will stand still on this point. So no motion at all. You can't move there. You can't get through this horizon because you will just stand still, just like that. And when this Earth swings to a point, actually that point sits somewhere else. That point sits in another space-time, and that is the central singularity. How all this relates, well, I don't think I'll be able to get the complete picture here in a short amount of time, but it's all by carefully studying what space-time looks like and all the equations, you figure out what that central point really means. It's another branch of space-time, so to speak. But let me first explain in physical terms what's happening. This is again this part of a circle that you see here is again the horizon of a black hole. And now I try to imagine what happens if an astronaut goes into the black hole. First, he goes to the left. He approaches the black hole, but then his clock will go slower and slower. Also, his heartbeat will go slower and slower. Everything will go slower. So the astronaut will slow down, and as seen from outside, he is never seen to actually cross the horizon. So he'll just be flattened by the horizon. After a while, you don't get any information from him anymore, but he never gets through the horizon. Now, the astronaut himself, when he goes to a black hole, will disagree. From his point of view, he will go right through the horizon just like that. His clock doesn't slow down, and the reason is that his heartbeat slows down, his brain slows down, everything slows down, but the relative velocities stay the same. So his heartbeat stays the same compared to his watch, and his watch stays the same compared to his brain. So from his point of view, he just thinks he goes straight through. And now he can go through the black hole to the end, to the origin, and there he meets that singularity that we just talked about. But you see, you have to, when you look from different observers, you see different parts of that black hole. This is a quite confusing subject, and I don't expect you to grasp all the fundamental delicate details of the situation here completely. Never mind. Just remember that the black hole is a strange thing where time plays tricks on you. Let's keep it at that for a moment. So where is the astronaut going? Well, it's a bit difficult to explain. Let me very roughly show you another metaphor, a comparison, and draw the region near the black hole horizon in a different way. Here you see lines. These lines here are equal time lines. So for distant observers, you have to compare this time with that time, that time, and here this time, that time, that time. Time runs in a double direction, but the equal time lines come closer together whenever you come close to the horizon. This means that very close to the horizon, the clocks go slower because these lines are much closer together. So, so for a distant observer, the clock here goes at a constant speed for the local observer, but then when the lines that show a time for the distant observer are much closer together. So a distant observer ticks faster than the local observer. But here something crazy happens. Actually, this is still a regular region of space-time, but the coordinates we use, the space-time coordinates, are just singular. So we say this is a singularity that's not singular in the physical sense, but only mathematically when we describe this space-time using coordinates. And here I can use a nice metaphor, saying we have something similar in another curved space, which is planet Earth itself. The surface of the Earth is curved. So to indicate a spot on the surface, we use coordinates, and then we use longitude and latitude. And whenever you give the longitude and latitude of a point, you indicate where on the surface of the Earth that point is. However, at the North Pole, something crazy happens. The longitude of the North Pole doesn't make sense anymore because all these vertical lines here, convene in the same point there. Now here comes my polar bear, and he walks on the North Pole, and right in the center of the North Pole he sits there for a moment, not realizing that's exactly the point where all our latitude lines combine. So what's the latitude of this polar bear? He has no latitude. But of course the polar bear couldn't care less. He does things that polar bears tend to do on the Arctic. So he doesn't even know that there's any problem with his position, because he knows where to find the next piece of ice and his food and so on. So don't worry about the polar bear. But we worry about the polar bear. We want to say where the polar bear is, because the coordinates that we're using make no sense at this point. That's also the situation near the black hole horizon. We send the polar bear to the black hole horizon. He will see nothing extraordinary happening there. He'll just go straight through to the other side. But what is the other side? There's a region 1 here and a region 2 here. If you look carefully at these equal timelines, you see that the equal timelines, here they go upwards in time, here they go downwards. So time is running backwards in this region. What does that mean? So now you have the problem of physics. Time running backwards, I'm lost. right? So that's now a situation, and now we want to understand how laws of quantum mechanics are under this situation. Quantum mechanics tells us what happens when particles are subjected to forces. And elementary particles do very strange things when they're subjected to these forces. And quantum mechanics does not yet tell us how gravity reacts when quantum mechanics works. So now, when in order to investigate the situation, the best, we will first ask the following question: under what circumstance is the gravitational force as strong as it ever can be? So this question has a rather surprising answer. The answer is in tiny black holes. Why tiny? Well, the gravitational potential lines are then quickly following each other from very large to nothing at all as a function of radius. So since the radius is very small for small black holes, the gravitational field, which is the gradient of the potential field, is very big. So the gravitational field is strongest near very tiny black holes. And trying to understand black holes, as I said, is pretty difficult. Trying to, it's also hard to imagine how tiny black holes can form, but never mind that. Because Einstein's equations tell you that there are solutions that form very tiny black holes. The Einstein's equations do not tell you how to make such a solution. So we can't do the experiment. We cannot actually make tiny black holes. We don't have hardly enough energy in our subatomic particles to do that. So we can't make them. But we can have theories about that to make them. Now, if you think that black holes are crazy objects, and I imagine some of you think this is too crazy, this isn't physics anymore. And yesterday I was talking about quantum mechanics. Many people said quantum mechanics is so crazy, that isn't physics anymore. Now imagine what happens if you combine the two. You get even crazier physics. But for theoretical physics, this is out and out. This is the real thing where we can enjoy ourselves. But how do you do that? Well, let me first tell you something about units of physics. There are three fundamental constants. Constant of quantum mechanics. Planck's constant controls everything quantum mechanical. It tells you that momentum, that is kilogram times meters per second, that's momentum, and distances, which is in meters. The product of momentum and the position is controlled by a commutator, and that comes with Planck's constant. So Planck's constant is expressed in kilograms meters squared per second. Now, Newton's constant also has units in cubic meters per kilogram per square second. It's a strange way to express the constant, but that's really what you need to do. In just these units, this constant has been measured quite accurately, and there's a speed of light, 300,000 kilometers per second. Now, all these three constants have different dimensionality. There are different combinations of seconds, meters, and kilograms. If you try to compute them in such units, we call those Planck units, where the combinations are such that you either get something with the dimension of a length, or you can get something with the dimension of a mass, or something with the dimension of time. And in these particular combinations, you get a length unit, a mass unit, and a time unit. These are more fundamental units of physics than the units we use now. Why the second? Well, second were defined in Babylonian times, so seconds are not really scientifically well defined concepts. And also grams were defined originally in terms of a standard kilogram that was kept in a museum in Paris. And the time, okay, now we can use time as by, well, centimeter was a unit meter at some point. So those are not the most fundamental units of nature, but these are. So 10 to the minus 33 centimeters is a very fundamental unit of time. And this is a fundamental unit of mass, and this is a fundamental unit of time. They are ridiculous units, because this is much, much smaller than any elementary particle. This is much heavier than any elementary particle, but smaller than the usual masses we work with in physics. This is a ridiculously short unit of time. If anybody wants to sell you a processor which makes more than 10 to the 44 steps per second, you shouldn't buy, because he's cheating. You can't have something switch that fast in physics. So this is probably the fastest switching time that you can imagine. This is probably the smallest distance you can imagine. And this is a very interesting unit of mass, 20 micrograms, something in between. The mass of a small grain of sugar or a big mega unicellular animal. But these are more fundamental units. We can think of a black hole as small as 10 to the minus 23 centimeters, a little bit bigger than that, and as heavy as 20 micrograms, or not the mass of the sun, or 10 times the mass of the sun, no, micrograms, and not the size of an atom, but 10 to the minus 23 centimeters, which is 10 to the minus 16 times sizes used in the standard model. So that's much, much smaller than the standard model units. And now we can try to imagine what happens with such black holes. The quantum fluctuations that we then can try to calculate, because we try to use the laws that you know to calculate what happens in these circumstances. So one of these laws is the quantum fluctuations. And when you compute the quantum fluctuations, you find that the quantum mechanical effects that you can compute do something very, very strange. And the first to discover how to do that was the guy in the center of this picture, Stephen Hawking. Here you see him standing between Einstein and Newton. You might ask, how can he be pictured together with Einstein and Newton? Because Einstein was dead before, Hawking was still very young, and Newton was already dead for several centuries. So what happened to space-time that made this picture possible? But as you know, Stephen Hawking knows everything about time warps and so on. So he figured a way to get this picture together with Newton and Einstein. But in reality, of course, it wasn't about that. This was an episode in Star Trek. Hawking was playing a short role in Star Trek, playing Hawking. Both Newton and Einstein were played by actors, but Hawking played himself. Hawking discovered the following thing, that yes, a black hole, whenever you throw something in, the gravitational pull is so high that these things will go right through the horizon and never come out. There's no physics allowing these things to come out. However, elementary particles do come out. They come out because of vacuum fluctuations. Hawking managed to compute those vacuum fluctuations and to discover that yes, particles come out. But now you can also ask the opposite question. Suppose I run this picture backwards, then the particles that come out are going back in, and the particles that went in will come out. So now you'll see that somehow things will come out of this black hole. And you can now ask, of course, how does all this happen? How can you explain this? Well, Hawking understood his calculations very well, so he could also explain why this comes out. And basically, it has to do with the way observers experience the vacuum state. It's very important to talk about observers and about what they observe to understand what's happening there. Remember that I said that crazy things happen with the notion of time. But the notion of time is crucial to define what energy is. Because time and energy are quantum mechanically conjugate to each other. So energy of all the quanta is related to the frequency of the field. The frequency, of course, depends on how many ticks something makes per time unit. So energy has everything to do with time. Now the vacuum state has everything to do with energy. Because the vacuum state, by definition, is a state nature can be in if you can't get any energy out of it anymore. Then you have the lowest energy state. That's the vacuum. However, if two observers disagree about time, they disagree about energy, and therefore they also disagree about the vacuum state. So one observer says, I see the vacuum, the other says, no, I see particles there. And at first Hawking thought he was making a silly mistake. He couldn't even define what empty space was. He felt very stupid. But then he realized that he wasn't so stupid after all, because he could compute how many particles are produced this way. And he found that the black hole behaves as a light bulb. It emits particles, but in a way that's totally under control. His equations tell you that the light bulb has a certain temperature, while this black hole has a certain temperature, and it emits radiation proportional to the temperature to the fourth power, because radiation goes at temperature to the fourth power. So the temperature is now the number you calculate, the distance especially found, and that means a little less than 10 to the minus 7 Kelvin for a black hole equal to the solar mass. But the lighter the black hole is, the heavier the higher the temperature is. And that is a very interesting equation. The equation tells you that when a black hole emits particles, you expect it to also lose that energy. The energy goes into the particles it emits. The black hole loses energy, therefore it loses mass, it becomes lighter, and now you see that now becoming lighter, the temperature will increase. If the temperature of the black hole increases, the radiation will increase by the fourth power of the temperature, so it's much faster. Even though the surface area decreases, the radiation goes with the fourth power of temperature wins. So the total amount of radiation will increase when the black hole loses these particles by the radiation. That will lead to a catastrophic situation, so the whole black hole will explode. Hawking then asks his astronomy friends, do you see flashes of light in the sky? Because I'm predicting now that a decaying mini black hole will leave a flash of light. You can see it from light years this distance. You have to calculate how much energy there will be in one of these flashes. Quite considerable. You will see light switches all over around you in the universe. Astronomers told Hawking, yes, we see light switches all the time. So Hawking was very excited, but then the astronomers told him that yes, these flashes that we see, they are correlated to galaxies. At the center of every galaxy, we expect a black hole to sit, every now and then these black holes flash. And that's called gamma ray bursts. And so those gamma ray bursts are exploding. Actually also, there are black holes absorbing something else, or stars collapsing into black holes, something like that. But these are much more energetic processes than Hawking was imagining. He was thinking in terms of light years, not in terms of billions of light years. So these gamma flashes, unfortunately, will not Stephen Hawking's particles decay. I will watch a little bit my time. I hope. Okay. I'm trying to keep now things start to get more interesting. The question is, are black holes elementary particles? Are elementary particles black holes? Well, yes and no to both questions. In a sense, particles and black holes behave very similarly. Particles can be made when other particles combine. You can make a heavy nucleus by having protons and neutrons come together. You make a heavy particle. Some of the nuclei can decay again, so they can emit particles. So from left to right, there's a process where particles may convene to make a black hole. The black hole is lying in the center. Then the black hole can decay by some flash, some decaying Hawking radiation at the end. Now you can also read this picture backwards in time. So now you see that this picture looks very much symmetric on the left and right, in this case. Symmetric on the replacing time and minus time. You see the same thing. You see the particles come together to make a black hole, and then the black hole decays again here. So there's some symmetry of time here. You can use that symmetry to do something very interesting and useful. And that is, I don't know how many physicists here have actually calculated physical processes in quantum mechanics. When you use quantum mechanics to calculate some property of a particle, like its decay time, how much time does a particle need to decay? And how do you do it quantum mechanically? What you compute is a quantum amplitude, you square it, and then you get the stability of the particle, how much, the number of decays per second. So to get that right, you have to multiply the volume of phase space. That's called Fermi's golden rule. You need how many different ways can the particle decay. For every single decay, this amplitude square gives you what the probability is. But in total, the probability comes proportional to the number of states it can decay into. That means you get the volume of the phase space of the final state, not the initial state. That's one state only. But the final state can be many states, and so you have to do that. But now, if you compare this process forward and backwards in time, suppose that the amplitudes for both cases are the same. So quantum mechanics is symmetric on the time reversal. Then the only thing different is the volume of phase space of the final state. But when I switch time to minus time, the final state goes to the initial state. So now I can say something non-trivial about phase space of the black hole. And the nice thing about this argument is, we did not know what the phase space of a black hole was. Well, now we do, just use this argument. And we find that the black hole phase space looks very much as if the black hole consists of little squares attached to its horizon, every square having roughly the square of Planck length as a surface area. And on every sphere there's every little square there's one Planckian bit of information. One bit of information per Planck square. And that's the total number of states the black hole can be in. And it's a very nice calculation. When you think of the black hole as all these squares going all up, they follow some equation of motion, we don't know what it is, but altogether that describes the behavior of the black hole in some abstract sense. So this was a good starting point to study the black holes. And we call this holography because it looks as if we are describing the happenings in a three-dimensional universe in which the black hole is embedded, as if it was all depicted on the surface area as a two-dimensional surface. So there's a link between three-dimensional space-time outside the black hole and two-dimensional space-time on the horizon of the black hole. So this is where the word holography was first coined, and we later realized that holography can be used in many ways in theoretical physics. So we are now in a position to compute everything. We know what the origin of these particles is. We know how many states black hole can be in. Now let's fill in all the equations and solve how the black hole behaves under laws of quantum mechanics. Now we see there's a little problem. It doesn't work. So this picture is a nice, beautiful picture you can have in the back of your mind to imagine how the black hole behaves, but we can't compute it. And the reason is, we are very sorry, but gravity is a divergent theory, so we can't really solve all these equations without running into outright contradictions. So we are missing something. We are like this rat. We thought we found the right ladder or switch to get this peanut, but we still can't get it. So we have to do something smarter than this. This is called the black hole information paradox. The point that there's information going into the black hole, there's information going out of the black hole because it emits particles, but how is the information out related to the information in? That's the way I like to phrase the paradox, but other people say that no information can get out at all. Well, let's see about that. But the whole picture that we have here is that somehow the particles going into the black hole goes through the wormhole to another universe. That's how Hawking likes to draw his pictures. The black hole going in, go to this other universe. The particles coming out came from the horizon. So the particles going out cannot be directly related to the particles going in. He thinks, I thought. But now there's one person, not besides me, who said, "Now, this cannot be right. There's something fundamentally wrong in our considerations here." Leonard Susskind wrote a book about this called The Black Hole War. He depicted the situation as he was having a battle with Stephen Hawking. Together with me, Leonard Susskind and myself and a few other physicists in particle physics were fighting against the other side. Stephen Hawking and some of his friends who studied general relativity thought that the black hole cannot allow its information to escape to the outside world. So we had these strong disagreements. I wouldn't consider this to be a war, because we're all friends and we have discussions and we have heated discussions, yes, but we're not fighting each other, we're fighting each other's arguments. But still, there was a fight going on. And what could the answer to this problem be? And one answer Hawking already gave is that he said, sorry, black holes themselves do not obey quantum mechanics. This we found very strange, because he used quantum mechanics. He arrived at black hole with particles. Now he gets the derivation, and then he says, now the starting point is not true anymore, quantum mechanics doesn't hold, there's something wrong here. Then you could say, well, maybe the information comes back when the black hole dies. So all the particles have evaporated out. But when they evaporate out, the black hole doesn't disappear, but leaves a remnant. That violates time reversal symmetry, but never mind. This remnant must be there, but it contains infinite amount of information, and it disobeys everything you know about physics. I didn't believe that at all. So, and Saskia is also unhappy with these remnants. So, the most reasonable answer is to think that the information comes back. It comes back from the Hawking particles. Hawking particles also carry information. Why not use that? Why not say that the ingoing particles, they deposit their information on the outgoing Hawking particles? But then the argument was, yes, but only at the final Hawking particles will do that. It only comes out at the very end. Now, people like myself and Saskia will say, no, the information comes out all the time. And as soon as a Hawking particle comes out of the black hole, it carries information. And that is part of the information that went in. If you look carefully at how much information can go in, you find that's roughly equal to the number of total number of Hawking particles that comes out. So every Hawking particle carries out with it a certain amount of information. So originally, Hawking was this argument, then later Hawking had that argument, or see something wrong here, Hawking around 2015 there, and then we around 2015, Hawking says yes, all the information does come out, but only at the very end. But Saskia and I always maintain the last position in 1984, from 1984 almost more or less till the present, we had this position that the information must come out of the black hole immediately. So we don't know whether Hawking will continue to have that energy. Now, string theorists say they have all the answers. So they see the black hole as a stack of higher dimensional objects called deep brains. And the way they describe the interaction with deep brains is that they mimic the behavior of the black holes. I'll write it down when we sort of over, but I still got a few things to say. So,
Please go.
okay, just the way in string theory black holes are pictured is that they have equations for strings in the vicinity of a membrane. Those strings actually represent space and time themselves, so also the way membranes fluctuate. So all the dynamical property of membranes is controlled by these strings, and together they obey equations very similar to black holes. So they say this is a black hole, and they say the black holes, like described this way, do obey all of quantum mechanics. And so the question now is, where does this apparent paradox come from? How come that if you try to understand particles going into the black hole, you see the information disappear? How does it come that string theorists see the information coming out of the black hole? Isn't there a contradiction here? I still think that the solution has not yet come, not with this argument, not with our argument of the question principle that the equation should come out. Yes, it should come out, but do the equations say so? And the string equations say so, but they don't tell you what the observer sees when he enters into a black hole. So that's also not the complete answer. So the real question is, how is information properly processed? And although many people believe that their theories provide the answer, I've always maintained that no, if you look carefully, that the theory does not yet contain the answer because there are direct contradictions. And the contradictions come if you see how does the information, how is the information imparted from the ingoing particles to the outgoing particles. Actually, that answer is rather easy. Ingoing particles go like that. Now, ingoing particles can go like this. The outgoing particles can go out like that. And in between, there might be an interaction. So the ingoing particle and the outgoing particle actually interact. All interactions can be handled perturbatively, so you can start your theory with no interaction at all, but not the gravitational force. The gravitational force is very, very strong. And the way you can actually compute the gravitational force. And you find that if a particle goes in, it drags along the particles outside the black hole, which want to go out as Hawking particles. They take some time to come out, so they are queuing up here to get out of the black hole. But these particles queuing up to get out are being dragged along by this ingoing animal, and so some of these particles are sent back. So that's a big difference. That's how the information of the ingoing particle can totally affect the particles outside of the black hole. I'll skip the next lecture. And then say, but then there's a problem. The problem is that this theory relates position of the outgoing particles to the momentum of the ingoing particles. And whatever you know about quantum mechanics will now tell you, position and momentum do not commute. You can't measure both of them accurately at the same time. Quantum mechanics is going to spoil this picture. Well, it really says if the ingoing particle is in a sharply defined wave function like this, the outgoing particle will be in a very wide wave function. That's because the outgoing particle, if the ingoing particle is in the position state, the outgoing particle is in a momentum state. And now comes the problem, the momentum state spreads over region 1 and region 2. Here time went forward, here time went backwards. How do I handle this situation? And that became the real problem. The solution to the problem came by saying that the outgoing particles are not only characterized by position. Their position is everything. If you say that you send in a particle, if you send in many particles, you can affect the position of all the outgoing particles. So taking all the outgoing particles, they are defined by the ingoing particles by saying that their position is defined by how much momentum the ingoing particles actually bring in and how do they replace the outgoing particles. So all this works except, and now you see the problem very clearly, you see the problem that the particles are going through a wormhole, and what happens to the ingoing particle itself when it goes through the wormhole. So one question is the outgoing particle sits in region 1 and region 2, and region 2 was something inside the black hole. So still that information is being left out. It's missed, so not everything is right here. If the particle is in the black hole, it's still lost. So something is still wrong about this picture. There was exactly one answer, a spectacular answer. I thought that if you apply theories of this sort, and I'll skip some of the details of the argument, but I'll just talk about what we normally have. So remember that he said that the broader black hole now needs other universe describing property. Now, here I have universe 1 and universe 2, but where's universe 1 and where's universe 2? Universe 2 cannot exist, because you can't just create a universe out of nothing. So when something forms a black hole, we have to first explain where universe 2 is. And now, the spectacular answer is universe 2 isn't there at all, it is just the other side of the black hole. How do you understand that? If you do that, by the way, you get the conservation of quantum mechanics completely. And now you can describe the length of the outgoing particles uniquely in terms of the ingoing particles. Now you have the one-to-one match between in and out. This way you can preserve the information. But what does it mean for space-time of the black hole itself? Well, the black hole, the universe used to consist of 2 parts. That's impossible, because we can't create a universe out of nothing. But you say, no, the second universe will just be a mimic of the previous universe, but we say that we identify the 2 opposite points on the horizon. So we identify this point with that point. And so if you enter into black hole, say from the back, I go here and I try to get across the horizon. But then instead of going to this space, we go to this space. So all of physics takes now place only in half of the universe which had been before. If at the horizon itself you identify the opposite points. Identifying the opposite points is mathematically easy. That is with one stroke of the pen, that's in the equations. But you have really divided the whole universe by 2. You have left out the redundant piece of the universe which have in the equations. And this is amazingly simple to realize in the equations. And this restores the quantum information just completely. So now we have one ingoing particle sent into as one outgoing particle. The the relation is 1 to 1. So now you have restored the quantum reality of the whole picture. Now we have a relevant way of describing a black hole. This is another way of drawing it. The black hole really is a region of space-time, but there is even no space-time inside. In fact, if you enter the black hole at this cross, you immediately re-emerge at the other side. If you enter the black hole from here, you re-emerge there, and so on and so forth. This is a picture that makes sense, and this will have the consequence that you have to modify your picture of space and time. The space and time, are no longer behaving the way they should, but they are normally doing. But now we have these empty regions of space and time, and in describing everything in terms of black holes and considering elementary particles also as black holes, you get these regions everywhere, and space-time becomes a foam-like structure. People have been fantasizing about foam-like space and time before, but now you see it happening out of various physical equations that this has to space-time has to form a foam. But that will put everything about the standard model on loose ends. Because now we have to argue again, how do particles move in this universe? I don't know. I only think that now we find that the black hole and the laboratory as a theoretical laboratory has shown to us how to do the space and time itself. And this is what I want to end. I went way too far beyond my time, so I apologize. I want to say something about this last, more spectacular ideas that we have now about how black holes affect our view on space and time.
Thank you very much.
And we have time for some questions. Felix?
Okay, can you go back one slide or two slides? No. Yes, okay, so let's assume this is true. How would black holes grow? Because then you say like, okay, when they form, they just stay the way they are and they're just a bridge between some kind of space.
So we also need a revision of the question how a black hole actually forms. The easiest way to describe a black hole being formed is to take a shell of matter, like an eggshell, and the shell also attacks itself, becomes smaller, 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 and then forms a black hole. Inside the eggshell, there is empty space-time. It's perfect vacuum. Nevertheless, the horizon opens up in that point. The horizon opens up, it starts out very, very small. When it's very, very small, there should be an alternative way to describe that space-time in terms of regions 1 and 2, which are such that if you don't them, you will invert time and you go from one to the other. And that's a difficult picture to visualize, but in principle, I claim now that there should be this manipulation that has an alternative way of describing what is normally vacuum space-time. So the vacuum itself should allow such a transformation to take place. And then you get the first picture of the black hole is just that one particle goes in, one particle goes out. And it's just like a fancy particle interaction. But as soon as the horizon grows, you have to apply the laws of space and time itself. Remember, on the horizon, time stands still. So as soon as the horizon opens up, you're describing the entire lifetime of the black hole in one flash. So the local observer sees the entire lifetime of the black hole in one flash. That includes the black hole long after it was formed. But it means that the picture that you have is also a mathematical transformation of space-time to another space-time. We should study, and that hasn't been done yet, the total set of laws about how to transform space-time into something different. All that has not yet been properly included in this theory. So your question is a well-posed question, and I only have a partial answer. That is why my answer is so long, because it's not yet a complete answer.
So, more questions?
According to your view, in which information is recovered, is there a regime in which Hawking's results are valid?
Yes, because the way Hawking treats what an observer sees is that observer sees two spaces. One is a space that you're all familiar with, or a space, but then there's a space behind, which we don't see. Therefore, Hawking says, what you don't see, you have to just ignore, of course, but you have to average over all possibilities that are there. So when you calculate what happens, you calculate, okay, you see what the particles do at our side of the horizon, you don't see what the particles do at the other side of the horizon. They may do anything you like. The probability of the particles doing this or this or that is the probability you get if you sum over all probabilities for these things you don't see. Now, Hawking imagines those to be something inside the black hole. I'm saying there are not things inside the black hole. You're averaging over the other things you don't see. Actually, what sits behind on the other side of the black hole, you also don't see. So now you're averaging over that. If you have detectors that can see both sides of the black hole at the same moment, then they deviate completely from Hawking, because they will see entangled particles, and Hawking predict they will be totally unentangled. So you'll be able to experimentally check whether Hawking is right, whether this theory is right, by having detectors at opposite sides of black holes and see whether the particles coming out are entangled or not. This you can measure experimentally in principle. But if you don't look at the other side of the black hole, Hawking's prediction becomes identical to this prediction. So there the theory is agreed.
So you mean you get thermal radiation?
Yes.
And entangled particles, would be observed if you are very small black hole? Not.
Well, the point is, if the black hole is not very small, the radiation intensity becomes extremely weak. So to measure that they are entangled is going to be hopelessly impossible. The rule of thumb is the size of the black hole. The sun, if the sun would go into a black hole, it would be 3 kilometers in size. That would be the mean wavelength of the radiation. Now imagine thermal radiation where the mean wavelength is 3 kilometers. That's very low temperature. And it's radiation of literally radio waves. Thermal radio waves is extremely weak. So weak it's unlikely that you'll actually observe that, let alone whether the photons on both sides will be entangled.
So isolated black holes in the vacuum are reflection symmetric, but in astrophysical context, like merging black holes, that ceases to be true. So in that case, what do you mean by the other side?
Well, the treatment of merging black holes is very, very much more difficult, because that's a time-dependent background. And now you analyze this again. But we start with if you start with saying these black holes are far away, then you can still treat them as individual black holes. They know exactly what to do. When they merge, these horizons will merge, and I guess that description will be a lot harder technically to understand, certainly to do the quantum mechanics of the horizon. In fact, there is a puzzle there which I have not resolved, only recently discovered as something which is worrying for this theory. That is that if large objects fall into a black hole, it seems that they deviate considerably from the classical argument. So if a large particle falls into a black hole, it causes repercussions on the other side of the black hole due to this identification, which may not be purely quantum mechanical, it may be partly classical. In that case, the theory would give more substantial deviations from classical calculations, even though I'm talking about quantum effects. The effect will even be visible in the classical limit. This is not yet resolved. I don't know what the correct answer to that question is.
So by large particles, you mean macroscopic objects?
Well, yeah, or I think of meteorites or something that is no longer quantum mechanical.
I mean, we see stars, tidal disruption events are stars falling into black holes.
Yes, because in principle, the laws of physics outside the horizon stay exactly the same. So the tidal forces would be just like tidal forces are, yes.
A very last question.
exact concerning the identification of polar points, and it can be extended to rotation of black holes, Kerr black holes, if you have difficulty.
Yes, I don't know if you know about the Kerr black holes, the Kerr Newton solutions on, but they have perfect cylindrical symmetry. So yeah, you always know exactly what the antipolar points are in that case as well. So I think it goes through unchanged for the Kerr Newton black holes. I'm not totally sure there, because I haven't actually done the calculation. But I don't see what else can happen in the case of rotating black holes, then also the identification of antipolars.
Thank you.
Okay, so if there is no any other question, so thanks again for all these